In this example, we are given a first-order transient circuit that contains a single storage element, this capacitor in here. And what we are being told is that switch has been closed for a very long time, and at time t equals 0, what we do is we open that switch. By opening that switch, we're pretty much basically eliminating these two elements. And what we're being asked to compute is this V0 across the 2 ohm in here, which is not the same voltage across this capacitor in here. And if we take a look at the sources that we have, all sources are DC sources, so we can either write the differential equation that describes this circuit and just solve them, or we can just use the general solution method. And I'll go ahead and just solve this general solution method. And since we're being asked to compute the V0 in here, T, and not the capacitor, I'll go ahead also and just show you what the voltage across this capacitor is as well, just to show you the differences in terms of initial condition and final condition and so forth. So let me get started with that. So the first thing I'm going to do is I'll go ahead and just basically write the equation for the first order, or the solution for first order circuit looks of this shape. So we have some sort of a variable. We need to figure out the final values, the initial values, and maybe the tau. And that's what we're going to be doing. And we're going to do that for V0 of t and Vc of t. So what we need to do is we need to find the initial conditions, the final values, and so forth. So let's start by the initial conditions. So we're going to do the initial conditions. Okay, conditions, and the initial condition conditions. Okay, can be at t equals 0, or maybe t equals 0 minus, or maybe t equals 0 plus. So it depends. And as it turns out to be, for this particular equation, what we should be targeting is this one here, which is t0 plus. T0 plus is the time exactly right after you switch in here. It's still initial. Nothing has moved exactly at 0. It's just a tiny bit after the 0. If you are computing Vc of t, well, all of these three will be the same and things will be easier. But for V0 of t, you will see, and I will show you actually, that the 0 minus and the 0 plus are not the same values. So this switch here, the jumps are allowed across a resistor, but not across a capacitor. So let's get with that. So the first thing I will do is I basically will redraw the circuit in here, and I'll redraw it in such a way that the capacitor is actually just an open circuit. So I'll assume for the initial condition right before switching what's happening before switching, and we'll compute these values. So let me just redraw that circuit. So the circuit looks like this, and for initial condition, I'll just basically take a look at the switch while it's closed. Right, and what I will do is I'll say, well, the capacitor has been, if the switch has been closed for a very long time, so what we have is we have no capacitor in here. We have an open circuit, because that's how the capacitor acts when all sources are DC. So what we will do at this point now is we will compute a couple of things. This one here is not V0t anymore, or V0t. We will compute it as V0, and I'm going to say 0 minus, it's before switching. Okay, basically right before we switch. And also I will do the following, which here we can call it Vc of 0, 0 minus, 0 plus, or 0. It's the same because the Vc opposes the change in voltage. So let's go ahead and just compute that. There's a few ways to do that. You can use mesh, voltage, whatever makes you more comfortable, or whatever you prefer. What I will do is I'll just basically write a nodal equation in here. And this nodal equation, you will see that this particular voltage in here is the same as the voltage V0 minus in here. Okay, so let me just write that nodal equation. So that nodal equation, I will say that V0 for 0 minus divided by 2. This is basically the current flowing through this resistor in here. Then the current flowing through that is just simply plus. That will be V0, 0 minus the 8 volt divided by 2. And then I will say plus V0, 0 minus, and this time it's minus the 12 volts divided by 1 plus 2 equals 0. This is basically the current flowing through these two. Of course, nothing's flowing through this, so that's it. So what we do is it's a single equation with single unknown. So that unknown is basically V0, O0, or 0 minus, is just simply 6 volts. Okay, and this is not necessarily the initial condition right after switching. They're not exactly the same. Okay, and we'll figure out with this value shortly. Now, how about the Vc of 0 in here, the one in here? So what we can do is we can also, I mean, there's multiple ways we can do it, but I think maybe one simple idea is just to say, you know what, I'll write a null equation maybe around here, or maybe it's not a nodal equation, it's just simply an equation. Basically, I'll just assume that this VC, I'll just say this current is equal to this current. That's what I will do. Okay, so what we will have is VC of 0 minus 12 divided by 1 plus VC of 0 minus V0 of 0 minus divided by 2 equals 0. I basically just wrote, it's simple, it's similar to nodal, well, it is nodal equation. This is the VC not VC0 is, or the initial for VC is what I'm looking for. So this one here is that minus 12 divided by 1, that's this current. And then this minus that, which we technically know what it is, divided by 2. So let me just substitute with the value of V0, not this one here. Let me just substitute the 6 in it. So what I'll end up with is VC of 0 minus 12 plus half of VC0 minus, I believe it's 6 divided by 2, which is just simply 3, that's 0. So that gives me that VC of 0, the initial voltage across that capacitor, will be just simply 10 volts. Again, this is the same as VC of 0 minus, this is the same as VC 0 plus, because the voltage across the capacitor does not change. So are we done with the initial condition? As it turns out to be, no, we're not really completely done, because what we're after in terms of V naught here is actually at 0 plus right after switching. So let me redraw the circuit right after switching. So what we have is right after switching is this voltage in here, we're going to call it V naught at 0 plus. So I'm basically drawing it right at 0 plus, right after the switch. So because the switch is open at this moment, what we have is the following. So the switch is open in here, so technically we don't have anything in here at all. We're not going to need it because there's no current flowing through that. While the C, or the capacitor, actually exists, what we will see is the following. The voltage between here and here is just simply VC of 0, or 0 plus, it's the same, which we know that we just computed to be basically 10 volts. That's what we know. So we know that the voltage here is just simply 10 volts. That's what we know. All right, so what do we need to do? Well, what we're after is the following. We're after this particular voltage, which is the initial voltage across the 2 ohm. And if you think about it, what we have is we have 2 ohm, and we have another 2 ohm in here, and we know the voltage across them, which is 10. So all we have to do is just use a voltage division. So voltage division tells me that you can simply compute V not 0 plus as simply 10, well, times half, because both of them are 2s, and that's basically 5 volts. And again, as it turns out to be, that the 5 volt is not the same as the 6 volts. So there will be a jump. Right before switching, it was at 6 volts. Right after we switch, it becomes 5 volts. That's not necessarily the final value, that's the initial value that we get. And now we move into finding the final condition. So finding the final conditions in here. Okay, so the final conditions is basically not at t0, but at t equals infinity, and we're going to be dealing with this capacitor as if it's an open circuit. So let me redraw that circuit for you. So that's the original circuit. So what we really have is we have the following. We're going to do this here, this one here. This doesn't exist, this doesn't exist. That's what we have. Okay, so, and then what we can do is we can say, well, between here and here, it will be VC final, because if we wait for a very long time, this is what it will look like. And this one here is V naught also final. That's what we're after. And we're after computing both of them. And it's pretty straightforward. We can just basically say, well, the 2, and the 1 are all in series since this is open circuit. And what I'm interested in is the voltage across the 2. We can just use voltage division. So what we can say is V naught final is just simply 12 times 2 divided by 2 plus 2 plus 1. And that's basically 4.8 volt. Okay. And similarly, if we're interested in just the VC of F, it's basically the voltage across the both 2's in here, which basically we can consider it as 4. So the VC, the final value across that in capacitor is just simply 12 times 2 plus 2 divided by 2 plus 2 plus 1. And that's simply 9.6 volts. So that's basically the final value. Again, you do not have to compute both the final value across the capacitor and the output in here or not. But I'm just doing it just to show you the differences between them. All right, so now we figured out the initial condition, the final condition. So what's next? Well, if you take a look at the equation, you will see that we're pretty much figured out this, we figured out this, we figured out that. What's left is the tau. So what we need to do is we need to figure out the tau in terms of RC circuit is just simply RC. So let's basically find, okay, tau, which is just simply RC. So if you take a look at the circuit, the original circuit, you'll see that what we have is we have several resistors in here, so we have to figure out which resistor to look at. And as it turns out to be, the resistor we need to look at is the R Thevenin resistor. So let me just make sure that after we wait for a very long time, that's basically what happens in here. So this capacitor, well, this is from the point of view of a capacitor, that's what we should be looking for. This particular point does not exist because the switch is open. And what we have is we have the following. We need to look at from here to here, what's the R Thevenin that we see in here. That's what we have to look at. And if you think about it, this is just simply an independent source in here, so we can just short it. I don't care about V Thevenin at this point, even though it's very easy to compute. I don't care about it. We can, but we don't need it. What we need to do is the following. What we need to do is we need to short this one here, and we need to look at the R Thevenin from this particular perspective. And what you will see is that R Thevenin is just simply the 2 and the 2 are in series, so that's a 4. And they will be in parallel with a 1. So what we have is 2 plus 2, and that's in parallel with a 1, and that will give me 0.8 ohms. So that's R Thevenin. So tau is just simply the R Thevenin that we just found times C, which I believe originally was 2 farads. Yes, it's 2 farads, okay? So what we need to do is we need to just say 0.8 times 2, and that's simply 1.6 second, okay? 1.6 seconds. And you can also say, well, 1 divided by tau is just simply 0.625 second to the minus 1. All right, so now we have found everything. Now all we need to do is just combine them together. So I will basically write the equation for V naught and the equation for VCF just so they can see them. So the equation for V naught of t, which is, let me just redraw that circuit in here or just paste it. So I'll basically start with this one here. So the equation for that is just simply we need the final value plus the initial value, which happened to be V at 0 plus for this particular case, minus V final, okay, the final e to the negative t, while t0 in this particular case is 0 divided by tau. All right, and we can substitute. So what we end up with is the following. We end up with V naught of t is just simply the final, and we can scroll in here. What we will see is that final is 4.8. So that's a 4.8 plus the initial that we found, and the initial right after switching the V0 plus, not this one here, which we found, which is 0 minus. Where is it? So what we need is not 0 minus, we need the 0 plus. So the 0 plus is 5 volts. I believe the 0 minus was about 6 volts somewhere. So we have it here somewhere, which is here. So I'm not after the 6, I'm after the 5. All right, so let's do that. What we have is we have 5 minus 4.8 e to the negative 0.625. This is the 1 divided by tau, which is t. So if you do that, V naught of t is just simply 4.8 plus, I believe that should be 0.2, yes, 0.2 e to the negative 0.625 of t. So that's basically what we're being asked to compute, and we were able to do that. Of course, the unit for that is just simply volt, and the time is t is exactly greater than 0, not greater than or equal to, because remember there's a little jump at equality with the 0. So if I'm to plot this, you can plot it and you'll see what it is. Let me just sketch it very quickly. So what it will end up looking, it will end up something like this. So initial value, remember the initial value in here happened to be 6 volts. So this one here will be 6 volts. And we can think about it as this way here. Basically at 6, it stays at 6 volts for a very long time. And then right at switching, right exactly at switching, what happens is it actually goes down to 5, okay? That's what happens, and you can substitute t equals 0 in here. This becomes a 1, so 0.2 plus 4.8, that's a 5. And then eventually what happens, it will go all the way to 4.8 but it'll go very slowly. So if assuming that this is 4.8, it'll actually go, eventually it'll just go very slowly. That's what will happen. So that's a 4.8. And that's what, well, if you substitute this equals infinity, that becomes a 0, so the final value is 4.8. So that here is the V naught, okay, of t. And that's basically the t. Okay, we can do the same type of analysis. Remember that VC of t in here, which we're not asked to compute, but we can do it. VC of t is just simply in here. Well, what is the final value? Well, we computed the final value to be 9.6 volts. So all we have to do is just basically say 9.6 plus, well, what is the initial condition? What's the initial value? I'm just writing the stuff I know already. Well, the initial value across the voltage, if you actually go all the way here, these are the initial condition, and that basically happened to be 10 volts. Okay, so we can do 10 volts in here. Well, we have this 10 in here, and we substitute VC of t will be just simply 9.6 plus 0.4 e to the negative 0.625 of t. We can also sketch, well, this is in volts, and this is t is greater than or equal to 0 because jumps are not allowed. I can sketch this one here. So if I assume that this is the t, and this is basically the V, for example, VC of t, what you will see is right around time 0, what we have is we have a, I believe it's 10, okay, and you can substitute this one here. You will see that this is basically, if this is 0, 0.4 plus 9.6 is a 10, so we'll see a 10. So before it was a 10, and after it stays a 10, there's no jump. And eventually what it will do is it'll actually reach 9.6 very slowly in here. That's what it would do. Okay, so 9.6, because if you substitute this to be infinity, that's what you will get. So it goes in here and then slowly, and that's basically VC of t. So I also wanted to show you the following. So this is the original circuit that we started with, and we said right after switching, what happens is we get rid of this branch because the switch has opened, okay? Let's do that here. So we switch with this branch in here. And what we have is we have the following. I have computed the value for this one here, for VC of t. That's what we have. This is the one that we saw in here. Okay, and I know exactly what it is, and what I'm really interested in is just V naught. And if you think about it, this is basically, I have a 2 and another 2 in series, and I know the voltage across them. It just happened to be an equation, which is this. So simply, you could have just told me, well, V naught of t is just simply half of VC of t. And you just go in here and just substitute it, and you'll end up with 4.8 plus 0.2 e to the negative 0.625 of t, and that's volt, and that's V naught of t. But of course, you should just understand that it's exactly t is greater than 0, not greater than or equal to. And this is exactly the equation that we got in here. So I could have just initially just targeted VC of t and just used it to compute it. It's voltage division, that's why it's half, because 2 and 2 voltage division is just in half. And you can do this. Certain exercises you can do these, others you don't. In this particular one, it just happened to be that, yeah, you could have just targeted VC of t, and that's about it.